Hello everyone, it's June the 21st. Well, a lot of learning today in the work about Python. And you think you have used Python a lot, you know a lot about it, but no, there's a lot, especially in the OOP realm. There's a lot of things there that I don't know. For example, the singleton, how to create a singleton, and then also the difference between, say, class method, static method, or when to use what, class variable versus instance variable, and how you can reconcile with those. Mainly, it's just in the work we need to change some code, and it was written in the pattern of a class, which has no instance. So every function is a static method, and the thing that it calls, the variables, is all class variables, so nothing can be changed. But now we need some variable in that class variable to be dynamic, and it's just not possible. It's impossible. I looked online if it's possible to make a class variable dynamic. The answer is no. And how if you can access an instance variable inside a static method? Answer is no. So it seems like whenever you need something dynamic, there's only one way, is you have to make the class instance. You cannot just use a static. But the use case we have, if we do instances, and there will be thousands, millions actually, millions of instances will be created for one function and destroyed. Create and destroy, create and destroy. Um, that might cause performance issue. So I think the only way forward is to create singletons. But technically speaking, this is not a singleton. It's each class can be instantiated by limited number of times. So we have like a key. So if this key has been instantiated, then it's instantiated. We don't instantiate again. So it's not really a singleton, but multi-ton. Wait, create some name. So using that pattern, I think we can reconcile with on both sides. We can reconcile the dynamic need, which would require instances, and we can reconcile the side where we cannot create too many instances, especially they are all repeats of themselves. So yeah, that's something new to learn. I haven't implemented it yet. Still in the process of discussing with the staff engineer whether this is a good way forward. I think he didn't really want me to touch that. He wanted me to use some very simple method, which works, right? Honestly, it works, but that code, it works just for now, and eventually it will be thrown away because we will have to deal with this static method issue one day in the future. Either we deal with them now, or we have to just deal with them in the future. So my point is, if we have to deal with it, why don't we deal with it right now? And especially the thing, it's not really. I mean, the current thing I'm working on, right? It has a very simple solution, which is a little bit spaghetti, but it's a simple solution. But the thing is, even if you solve it using the simple solution, you cannot push it to production because the production requires the underlying problem to be solved. And we cannot just like say wait until the underlying problem to be solved. No, we cannot just like solve it right now using a band-aid solution, and then in the future we have to solve it really. And then when we solve it really, we have to go back to the band-aid and then just to change it. And none of this will be reflected in the in the production. So what's the point of, like, we have to solve it anyway? Why not just solve it the right way, and then we can just get like both problems solved the right way? But anyway, so I'm still having the debate, and hopefully I can win the debate. All right. Anyway, let's move on to today's thing: kth largest element in an array. So that is, you don't have a requirement to not use sorting. No, so we just sort, and then I don't see how this one is any challenging. It's like yesterday's problem. Oh, it's so challenging. Well, it's challenging is not because the problem itself is difficult. Just I wasn't able to figure out a way to handle it until I read a hint. I think that's what happens in the first time when I solve that problem. I have to read a hint and then start from there. Now this one, if I'm not mistaken, is really straightforward. We just sort it, and then we return nums. Is that k? The kth largest, so minus k. All right. Yeah, I'm doing like we can say return sorted nums minus k. It's good. I mean, if it's really that straightforward, and we have time to solve one more problem, and we can end the whole thing really fast, because I really need to do this fast today. All right. So this one will be nums and k, and this one will be find kth largest. Okay, so that seemed to be, well, we'll throw some edge cases at it. Oh, this one will pass. We know. Also throw some edge cases at it. For example, 1 and 1. Right? I think that's the only edge case. Or okay, is one more edge case. 1 1 1 1, and then we say the third. If that passed, then that shall be it. Yeah, that shall be it. So what other methods are there? Why do I have something so fast and something so slow? I guess I was sorting it by hand. I don't know. I'm just curious to see what happened out there. This one is 2:15. Alright, so this one, 32 test cases. Oh, it's a quick select. Ah, what is this? I was trying to implement, but didn't implement. 32 is the same. Alright, so quick select. Locate pivot. So we'll random pick one. So what's the idea? Kth largest. So we randomly pick one. So pivot, or locate a pivot. And then what? We put a pivot, and the left we swap these, okay? And then if something is smaller than, if it's smaller, then we swap, okay? And at the end we swap the two. So we put the pivot in the right position. So we put the pivot in the right position, and then we return. If it is k, then we return. Otherwise, we. I see. All right, we shall code it. Come on. So that's why this problem exists. Quick select with a random pivot. Now, it is important to know if this is a problem. I mean, this is O(n) log n, right? This is O(n). So I would just go O(n) log n, honestly. But for training purpose, all right, let's do this. So we're gonna say pick pivot, right? And we have the left and the right, and now return an integer. All right. So what do? We say pivot equals rand int L to R, okay? And then we say nums L, nums piv equals nums piv and nums L. So we put the pivot in the first. And then we say j equals L plus 1. And say for I in range from j, right, all the way to R. So go all the way. And if nums I is smaller than nums j, okay? If this happens, if nums I is smaller to nums j, then we swap. So nums j, nums L. If this thing is smaller, then we say nums I, nums j equals nums j, nums I. Alright? So basically we say if any point this is smaller, then we swap. Right? It's smaller than this, then we swap. And after swap, j plus equal 1. So we move j forward. And if it's larger, then we, if I is larger, then we just move on. First small, then we'll swap. And then j will fall. So these are the j always pointing to the thing that's larger than nums L, larger than the pivot value. If it's small, we can swap. And then when it's small, we swap. Once we're done, right? Once we're done, it doesn't feel right. Shouldn't be the two meeting each other? Shouldn't be the j on the right side? And then j should be minus equal 1. Alright? So if this is smaller, if this is larger, then we this is not the pattern I know. So I'm not going to do this. I don't know this pattern. So actually I'm going to set j equal to r and I equal to L plus 1, right? Let me say while I is smaller than j. That's the pattern I know. And then we'll do the same thing. Say if this is smaller than L, so anytime if this is smaller, then we don't do anything. But if it's larger, right? If it's larger than, I'm going to say larger than equal to. It doesn't matter. If I is larger than this, right, then we swap with j. Because j is on the right side, right? We swap with j, So j gets something larger, so j gonna minus equal 1, right? J gonna minus equal 1. And I always plus equal 1. So if it's smaller, then we just keep moving, smaller, bigger, boom, swap, right? And actually, after we swap, we don't increment I. Because after swap, you might swap a small one, right? So you have to, you might swap a bigger one, and then you do the next one, right? And you'll swap again, and you'll swap. You just keep swapping. So eventually, these two will meet each other, right? And when they meet each other, is that so? Either I plus equal 1 is going to be this is smaller than nums, right? This is I is smaller, so I plus equal 1. Now they meet each other. Or I is larger than this, okay? I is larger than this, and then we swap, and then after we swap, j goes smaller. So after we swap, we just swap something to, so from position I, we swap something bigger, right, to j, and j minus equal 1. So that could point into the smaller one, but we don't know. That could also be the bigger one. So what do? When we get out, we want to know where to place, right? Where to place the pivot. So smaller goes here, larger goes there, larger goes there. Maybe we should put larger equal to. Maybe do larger equal to. Right, so j minus j will move when it's larger equal to. Maybe that will be good. Larger equal to. The kth largest. Nah, I think it's larger. If it's larger, I is larger than this, then we move. So when we don't move, right, we keep it, and then if it's larger than, so we will be able to move this, right, move this to the rightmost place, Okay, so the question now is, when it exits, what happens? If this is larger than this, then I swap these two values, okay? Swap these two values, and then j minus equal 1. So that could be still a larger value. Or I swap, this could be a smaller value. So this could be large, could be small. And if I plus 1 is if this is smaller than I plus 1. Again, it could be, so we have to check when they come out. We check I, right? We check I, see if it's larger or smaller. If the I is smaller than L, that means we need to do that. If it's larger, then we have to use, okay, so when we get out, we say if nums I is smaller, right, than nums L, okay, then nums L equals nums L and nums I, right? We swap the two because I is smaller, so we swap the two. Then we can return L. right? We return L immediately. L is the index. Is index where this one shall be. Else, if I is larger or equal to, so this is larger or equal to, then we're going to say nums so nums I is larger or equal to, so we have to swap. What if it's equal to? No matter what. It has to be I minus 1, right? I minus 1 nums L equals nums L and nums I minus 1. And I'm going to return L minus 1. No, to L, to I. And this is return I minus 1. Okay, so that's the pivot. And we say low array equals 0 and then len nums minus 1. So while L smaller than R, pivot equals to pick pivot down R, right? And we say if n equals len nums, if n minus pivot is equal to k, then I return nums piv. Otherwise, if n minus piv larger than k, okay? N minus pivot, n minus pivot larger than k. So pivot is too small, right? So we say we want the 2, but we got here so too small, so we need something bigger, right? Something bigger. So if we want something bigger, then we say L equals piv plus 1, right? That is something bigger. Else R equals piv minus 1. Well, I think only one side shall have, because I have a smaller than R. Which is smaller equal to, because I don't want to get out. It's guaranteed we will have a solution. Let's just try this. Okay, so far so good. We have a couple more like edge cases. That should be one. Oopsie doozy, that is not right. So this one doesn't work. Why? So that will be 0 and 0. Okay. Ooh, 0 and 0. Really didn't. Huh? I'll put it back. What's L? Shouldn't that be 0? Oh, I is already... I equals L plus 1. L is good, but I is not. Right? So we say if I is smaller than R, okay, so if I is smaller than R and, right, then we return this. Otherwise, we do I minus 1, which in the worst case scenario will, okay, so this one, oh, and then this one is not right. The hell? Smaller equal to. Okay. It feels more convoluted than the original solution. It is just like binary search. Let's see if this version works. Oh, it works. It works. Oh, when? But I'm pretty sure this is not the optimal solution because this is the optimal. You can see it's slightly different, right? I have piv, we have this. This is fine. For I all the way to R. If this is smaller, then we do this. And J plus equal 1. See, this surprises me. J and I, they both start at the same position. And then I keep going, right? If this is smaller, so if I is larger than, so J will stay in the small. I will get bigger and bigger, right? So I goes big. If it's all big, then it's fine. But whenever we find something small, we'll swap with J, and J move forward. So go all the way down, okay? Then J will be the, so J will always point into the last smallest one. I think that is the case. The last one that is actually not that small, the last one that is bigger, because as I move forward, right? As I move forward, if J doesn't move, that means it's all bigger than, right? And then we can swap and move forward. So every time J moves forward, we always move to an unknown territory. Right? We move to unknown territory. Actually, no, we always move to something bigger, because if it is something small, we already have swapped it. So we always move to something bigger. So at the last step, J has to minus equal 1 to do the final swap. Yeah, I think this is right. Easier than this one. Easier. Alright. Alright, let me just end it right here. I will see you guys tomorrow. Adios.